Rick, if memory serves, the Torino Scale, there's more going on than just a number.
Consequences versus probability. 0 is really good and 10 is a really bad day for the dinosaurs.
So recently, 2024 YR4 has been in the news. So it's green, yellow, orange, red.
Where we want to stay out of is the red zone of 8, 9, and 10, because those are the levels where you are certain of an impact. And YR4, if it misbehaves, it would go all the way up to 8 on the Torino scale. That would be its maximum.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck Nice. Chuck, baby.
Hey, what's happening, Neil?
All right, co-host, comedian.
Yes.
You know what we're going to talk about today?
What?
Oh, my gosh.
Go ahead.
Hazardous asteroids, Pluto, and Planet 9.
So are we saying that Pluto and Planet 9 are just now demoted to hazardous asteroids? Because, they were a planet. You knocked them down, humiliated them completely.
You're not over that. You still haven't gotten over that.
Well, no, and then it was like, okay, you're a dwarf planet. It's like, at least I get to be a planet. Now you're just like, you know what? Hazardous asteroid.
Well, while I have some expertise in this space, I don't have all the expertise I want for this show.
Okay.
So we went back.
Uh-oh.
One of my peeps.
Okay.
One of my people.
All right.
I got one of my people who invented the international scale to measure how hazardous an asteroid will be to life on Earth.
Okay. That is a hell of a quality to have on your resume.
I'm just saying, in the business card,
Yeah.
I tell you whether your ass is fried or not.
Yeah, that's amazing.
So let me introduce us all to Rick Binzel.
Hey.
Professor Richard Binzel. Rick, how you doing, man?
Hey, Neil, great to see you. Chuck, nice to see you.
Nice to see you.
Yeah, so you are retired now, Professor of Planetary Sciences at MIT, which stands for?
Massachusetts Institute of Technology.
Thank you. That took you too long to.
I was going to say something smart ass, but you saw me bridling myself.
Yes, you did bridle. You did bridle. And you are the inventor of this hazard scale, the Torino scale. We'll get into that in a moment.
Okay, I got my first question already.
All right, you're a co-investigator on OSIRIS-REx. Remind me, Rick, that was the mission that was that the one that did the touch and go?
Yes, OSIRIS-REx was the touch and go that successfully returned an asteroid sample to the Earth.
Back to Earth. So that's badass.
That's more than badass.
And we're going to find out if it had any bugs in it.
Yeah.
And of course, my boy has an asteroid named after him, 2873 Binzel, and that is not his password on his accounts. Okay?
No, sorry.
He tells me that's not his password. He's also a staunch Pluto lover.
Oh, really?
So we've had some dust ups in our day.
I could only imagine.
oh, put your thumb down, dude. So we're old friends. So we went to graduate school together.
Oh, wow.
We were in the same class in graduate school.
That's pretty cool.
That's pretty cool.
Yeah.
And
that was a previous millennium, too.
Oh, yeah, way back.
Okay. Since you were in school at the same time, what was the most advanced technological equipment that you had at your disposal when you were in school? Because that will give people I
got one for you. Ready?
Go ahead.
At the time, you were able to visit someone's house, dial a set of numbers to forward your phone number to their phone number so that if someone was calling you at home, they could still reach you while you were at your dinner party.
Oh, wow. So
that you get your phone number to follow you.
How telling. That's amazing.
Yeah.
It's
I thought that was good.
You can have your phone number follow you.
Correct.
You're forwarding your own calls to you.
Correct. Rick, what do you have an opinion on this?
You could connect from your home, you could connect to the computer on campus by literally dialing a phone, sticking it into a box that had 2 earmuffs to connect your phone receiver.
So the handset of the phone, yeah.
A handset of the phone into what was called an acoustic coupler, and you could talk to the computer on campus from your own home.
That was amazing.
That was amazing, huh?
Amazing.
At 300 baud, 300 bits per second.
Yeah.
Oh my God, that's awful.
We were not streaming videos back then.
That's amazing.
You published a paper at age 15? I forgot about that. What was that paper on?
It was on asteroids, Neil.
Oh, okay. He goes back.
Yeah, we had an experience of a camp run by a Columbia professor named Joe Patterson, and he just reached out to high school kids, gave them this fantastic experience that was formative in our careers. And so many of those students became professors and professional astrophysicists. Anyway, so it was a super opportunity, and I haven't stopped since.
There was a research project in that camp.
That's right. That's right.
Okay. So I attended the same camp, but not at the same time.
Not at the same time.
But we didn't know each other at the time. We get into graduate school, and we find out that the two of us, plus another person in our class,
We're in that camp?
all attended that camp. It was an astronomy camp called Camp Uranoborg.
Camp Uranoborg.
Do you know what Uranoborg is, historically?
I believe it's the Borg ship.
The Borg?
So when
Star Trek
when
Borg?
you're on the Borg ship, you're on a Borg.
You're on a
You're on a Borg when you're on the Borg ship.
Okay, that's a good one. That's good. No, but that's good. It was the Observatory of Tycho Brahe.
Oh,
Tycho Brahe.
Tycho Brahe. That's your buddy.
That's my man.
You like that
He got
dude.
all the data on the planets. And so it was a camp, and we lived nocturnally. We slept during the day and up during the night. It was totally geeked out. We're both 14 or 15.
Right.
Yeah, exactly.
So, Rick, one other thing about your time in graduate school, which betrays some of your affection for Pluto, is Rick made, correct me if I got this wrong, he made the first measurement of the light dimming of Pluto's moon going in front of and behind Pluto.
So Sharon transiting Pluto.
Correct. And that was the best evidence available at the time that the moon even existed.
Amazing.
And then, well, isn't that what allowed people to calculate a true mass for Pluto and its size and all of this?
That's right, Neil. When you have a body in space, unless you have something orbiting around it, you use Kepler's third law to calculate the mass of the primary or the mass of the system.
What's Kepler's third law, please?
Dude, why do we have to explain that to you?
Just because,
Oh, for other people. You want other people to know about it.
No, not me. I'm just saying some people might be wondering what Kepler's third law is.
All right. So Kepler's third law is a relationship between the orbital period of an object compared to the mass or the mass of the primary or the mass of the system. And so if you can measure the size of the orbit and the orbital period, you can calculate the mass of the system.
We got the mass for Pluto and it was way littler than people wanted it to be. Confess that right now on my show.
The mass of Pluto is what the mass of Pluto is.
Oh! Let me tell you something, Rick. You do great in Congress.
Or in court. That put you on Pluto's radar from Jump Street right there. So I was not surprised that he turned out to be a staunch Pluto lover his whole life because he birthed Pluto's mass.
Yeah, but by birthing Pluto's mass, you also birthed its demise. But go ahead.
So, Neil, I was looked at Pluto for 5 years. I actually spent about 10 or 15 years total working on the Pluto system. But we started looking to see if we could detect this moon around Pluto about 1980. And it was a 5-year search of looking for these transits, and that didn't show up until 1985. And then they were continuing from about 1985 to 1990. It's the same technique that we use for looking at planets around other stars, of course, transiting exoplanets. But this was planetary transits, and we were kind of doing it before it was popular.
Now, Rick, you just reminded me of something. There was a fuzzy photo of Pluto, and there was a little bump on the edge of the circular outline. It was still fuzzy, a little bump, and that was a hint. If we believe the photo and the emulsion, because back when there was authentic photographs, right? If we believe that meant maybe it has a moon. And I was just reminded that not all transits go exactly in front of the thing you want them to transit.
Right.
So if the angle is wrong,
you're not going to see it when you think you're going to see it.
So that's why you were looking for it and you didn't see it for 4 years because our sight line to it wasn't properly oriented yet. Did you know that at the time?
Neil, that's right. I mean, what we didn't know is we didn't know what that angle is, or the inclination of the orbit. And so we didn't know when the Earth, most of the motion around in this case was the Earth's motion around the sun. We just simply didn't know what the inclination of Charon's orbit, that's what we call the moon today. We didn't know the inclination of Charon's orbit, so we didn't know when it would become edge on to the Earth. And but going back to those bumps, that was 1978. Those were on glass plates. That's when telescopes. We didn't have CCDs. We didn't have those electronic detectors yet.
Back in the day.
Back in the day, you had to climb uphill in the snow both ways to get to the telescope.
No, that's when telescopes. Here's what you did: you put your head under a hood.
Yeah, this is the old man hour here. Okay.
So anyway, those bumps and those fuzzy images would move around, and it moved around with about a 6.4 day period, which we knew was the rotation period of Pluto. So it all made sense, but we really didn't know and make sure that it wasn't some funny photographic effect until we got those transits in 1985. And those first transits were just along the top edge of Pluto, along the pole of Pluto. And so it was the beginning of a long series of these transits that we actually used to make the first maps of Pluto.
Well, because you can say how it dims or brightens as Charon moves across it, so you get a blunt understanding of the reflectivity.
Exactly. So if it goes across a dark spot, the light doesn't change very much, but suddenly as the edge of the moon goes across Pluto and you get a big light drop, then there's really high albedo spot underneath.
Very cool.
High albedo.
Albedo.
I love that word.
Yes.
It's almost, do you albedo? I albedo.
Now that you just made it creepy. You just made it very creepy.
It's a fun word that gives no indication of what it means.
That's true.
Right?
Yeah, you would never know what it was.
Tell us about albedo, Rick.
Albedo is a fancy name for reflectivity. Something with a low albedo doesn't reflect very much light, and something with a high albedo reflects a lot of light. So ice has a very high albedo.
A lump of coal has near zero albedo.
A few percent, yeah, a few percent.
And a mirror or just a coat of white paint would have very near 100% albedo.
All right, this is starting to sound very racist.
Hey, StarTalk fans, I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcasts and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk.
Let me ask you this. A long time ago, I read this article, and I mean, it was long ago, and it talked about, because you just said reflectivity and albedo, it talked about how Pluto was so reflective the way it was that they were able to determine that that's because it was mostly ice, which means it was a lot smaller than they actually thought, because what you were seeing was more reflection than you were actual body.
If you don't know anything about a cosmic object orbiting the sun, you'll make an assumption of what its albedo might be based on other albedos that you have measured, correct?
That's right. So when you first discover something, you make a best guess at its albedo or reflectivity, and then maybe someday you get the actual measurements and you can refine it.
All right. So, what was your first presumption of the albedo of Pluto?
Probably around 20.
20%. Okay. And so, given its brightness, you would say, if it's that bright and it's only reflecting 20% of the light, it must be this size.
Okay.
And so now, given that it has an icy, more reflective surface than previously, its albedo jumped from 20% to what?
Into the 30s, maybe up to 40%.
Okay.
Oh, wow.
Yeah, factor two almost.
That's a big, yeah.
Yeah, so that's
a big deal.
That worked. Yeah. All right. By the way, you're in my Pluto book. I mentioned you. I don't know if you remember that.
I believe the actual words were, "Take that, Rick."
No, let's go back to asteroids. A big part of your career has studied asteroids.
Cool.
And you were at a conference in Torino, Italy, where you proposed a way to track how hazardous an asteroid might be. and it came to be known as the Torino Scale.
Which I have a problem with because I understand that there's 2873 Binzel, okay?
Mhm.
And that's an asteroid named after you.
Yeah.
Well, why wouldn't it just be the Binzel scale since you're the guy that came up with it? Why so humble, man? You gotta take it while you can get it. Okay? Grab the gusto and the glory. Like, we live in the time of Trump now, man. You gotta you know what I mean? It's the best scale, the biggest, the most beautiful scale. It's wonderful. Like,
It can measure
it
everything.
can measure everything, not just asteroids. It's used by plumbers. It's used by carpenters. It's the best. Like, but why not? Why call it the Torino scale and not the Binzel scale?
Well, it is wonderful, and it's the best.
Oh,
I love it.
Whoa.
Yeah, I'll just say the Torino scale, or how we talk about asteroids, is something that we have to do very internationally. And
Okay.
so the fact that it was adopted at the conference in Torino, gave it more of that international flavor. And that's
These are my people.
All scientists, you're all the same. Scientists are always sharing the glory
It's my people.
and sharing the wealth with one another and collaborating with one another.
Don't say that like it's a bad thing.
Do you know what world?
Collaborate.
Do you know what world you live in? Is what I'm saying. No, that's fantastic. I'm so happy for that. That's
Now,
great.
last I read up on this, but it's been a while, so forgive me if I misremember. This scale has multiple factors operating simultaneously, right? One of them is the risk that it will hit Earth, and two is how much damage will it create if it does.
Ooh.
Those are combined into this one scale. Is that correct?
consequences versus probability is
Nice.
the basis for the scale.
Rick, if memory serves, the Torino scale, there's more going on than just a number. So remind me what you put into it.
First of all, the Torino scale is a 10-point scale from 0 to 10. All right, 0 is really good, and 10 is a really bad day for the dinosaurs. And the way you calculate where an object falls on the Torino scale depends on the size or the consequences of what that object would be if it struck the Earth versus the probability, the current best estimate for the probability that it could impact the Earth. And so it's two dimensions, consequence and impact probability.
And is the scale pointed at specific asteroids that are out there, or is it just a generalization for any body that might come our way?
Well, it could apply to anything, but it really only matters for asteroids that have orbits that can come close to the Earth. If you're in the main belt between Mars and Jupiter, you're not going to bother the Earth.
So you're a zero.
So,
you're a zero on the scale.
Yeah, they're zero. They're zero.
Oh, how about the asteroid with your name on it? What's the hazard scale for that?
Oh, man.
Zero. Zero, I'm afraid, or I'm happy to say.
Yeah, I was going to say, because that would...
You don't want the asteroid Binzel come and take it out.
Binzel at an 8, and it's like, okay, this whole thing was rigged. He created the scale, and now the asteroid...
He's the one that's going to take us out.
Takes us out.
That's a Lex Luthor move,
Right,
right?
exactly.
Yeah. At the lowest level, things are green. You have a green level, which means, this is normal. We're going to find a lot of these. We're currently at that next level up, which is yellow, which just says these merit attention by astronomers. So that's what level 3 is merits attention by astronomers. And if the probability gets worse, we would go to orange, which means there's a possible threat here. And where we want to stay out of is the red zone of 8, 9, and 10, which means we have 100% probability of hitting the Earth, and now it's a matter of what would be the consequences. And those consequences depend on where the object lands. So we're in the yellow zone. We'd rather be green. And if we go completely to zero, that's just colorless. That's just a blank zero. And so we expect this object, the odds are greatly in our favor. We'll get it down to zero. We just have to keep watching it and refining that track and get the information we need to drive it down to zero.
So it's green, yellow, orange, red. 4 colors?
Mm-hmm.
Correct.
Got it.
Correct.
Very simple.
And zero is no hazard, so that it doesn't even get a color.
So recently, 2024 YR4, the 2 letters and then the numeral, has been in the news. By the way, it's one of, I think, tens of thousands of Earth-crossing asteroid. So this was one happened to be the one to talk about today.
Okay.
We saw that it had a 1.3% chance of hitting us. What does that mean if that number is given?
When you discover an asteroid, you're only seeing a tiny piece of the orbit as it's moving through space. And so, we'd like to project forward, extrapolate that position, for decades, if not centuries into the future, just to make sure that it's not going to intersect with the Earth. And we do that for every asteroid that's discovered.
He didn't say slam into Earth and kill us all.
Intersect.
Intersect.
Right.
It's a very dispassionate word.
Oh, without a doubt. Yeah.
Go on.
So we do it for every asteroid. Every time we discover an asteroid, we'd like to make sure that we know that one's on the good list and not on the naughty list. And, in this case, we know this asteroid in the year 2032, and in fact, every 4 years, it comes somewhere near the Earth. But we find in 2032, it's going to come close to the Earth, probably about as close as the moon or closer. And we simply don't have enough precision in terms of how well we know where that asteroid is precisely going to be in 2032 or other decades in the future to know for sure that it's going to miss the Earth. And so because we can't say we're certain it's going to miss, it gets a probability of intersecting the Earth. So that's just simply where we are. It's really that probability number is really a measure of what we don't know. It's not a measure of what we know. It's what we don't know because we simply haven't been able to track this thing for very long.
Here's something that might be new to Chuck. Were you able to get a pre-discovery image of this asteroid?
When we discover an asteroid that has some future chance of intersecting with the Earth, one of the tricks we can do is go back and see if it's shown up on in images that we've taken of asteroid searches, many years before. Because if we can find it, like that it was someone accidentally saw it 4 years ago but didn't measure it, that gives us another 4 years of an orbital length that we can use to calculate forward. And so these are called pre-discovery images. And I know people have been searching the records for pre-discovery images to get a longer track on this asteroid, but those haven't shown up. The asteroid 2024 YR4 is simply a pretty small object. It's probably about 50 meters across, something like what Tunguska, Siberia experienced in 1908. And, for the longest time, we never had the capability of even seeing these objects out in space at great distances. And it's simply our capabilities have just gotten so good that we're starting to see really small objects far away. And so we can start to make these extrapolations forward. This is just the first of probably many cases to come where our capabilities exceed the precision of computation. So we'll have lots of these cases, I think, coming along.
So I posted a short video in a series that we do called "What's Up with That," and that's where my producers say, "Neil, this is in the news. We should. What can you tell us about that?" I spent 5 or 10 minutes. I commented that when you have an uncertainty of an asteroid risk of hitting Earth, as time moves on, that uncertainty goes to one of two numbers. It goes to 100% or to 0 once you have a tighter and tighter knowledge of its orbital path. And so recently, it jumped from 1.3% to 2.3%. It's on its way towards 100. Rick, what's going on? Protect us.
And when do we need Ben Affleck?
No, it's Bruce Willis.
Yeah, know your disaster movie.
Yes, dude.
Yeah. Well, Ben Affleck was in that movie.
Yes, he was, but he wasn't the hero.
Yeah, but I like Ben Affleck.
Okay, fine. He was Batman. Don't confuse him with that.
Well, Batman I wouldn't call to save me from an asteroid. That is for sure. That's a Superman job, if ever.
If ever, right. So is this on its way to 100%?
Yeah, so Neil, as you just said, ultimately when we get the final answer, we'll know it's either 0% or 100%. It either hits you or it misses you. And the odds are greatly in our favor. We're about 50-1 right now that it's going to miss. So I like those odds. It turns out for this asteroid, the region of uncertainty is like this long spaghetti string that stretches from beyond the moon, basically all the way across the moon's orbit. And it happens to, part of the string happens to lie on top of the Earth. And so that spaghetti string, and we use Italian pasta because it's the Torino scale, that spaghetti string will shrink as we get more and more data that improve the track of the asteroid orbit. But until that spaghetti string shrinks and doesn't have the Earth underneath a piece of it, we can see that probability number bounce around. There's really no surprise there. And I'll just say that ultimately we'll get to the final answer, and that uncertainty will shrink to the size of a grain, basically a tiny grain. And so the chances are that when we shrink that uncertainty region or that spaghetti string down to a single grain, that single grain could be further than the moon. It could be somewhere between the Earth and the moon. But the chances of that grain being on the Earth are just that few percent.
Okay, but if it is on Earth, the grain could be on top of Hackensack, New Jersey, or Hoboken. Where you live?
Hoboken.
Hoboken.
And I thank you for destroying where I live.
Often when we think of an uncertainty, I think of a circle, and it's most likely to hit in the middle of the circle and less likely toward the edge. But what you're saying is, given its orbit and the orientations, the circle is now elongated, maybe to an ellipse, but this is a severe ellipse. It's so elliptical that it's a spaghetti strand. That's what you're telling me.
That's right. What we call the uncertainty ellipse is really just sort of flattened out into this very long string. It's like you take pasta and you keep stretching it and stretching it. And this uncertainty region has just stretched out into this long spaghetti string.
Yeah, but is it linguine or fettuccine?
No.
I thought it was linguine to start, but it's now getting so thinly stretched out. It's definitely spaghetti. And I don't think it's quite angel hair pasta yet, but definitely a spaghetti string.
Okay.
Torino strikes again.
Yes. And what sauce is with this? Well, I need to know. I need to know what sauce we're putting with this meal.
Yeah, that's a personal choice.
Okay. Okay.
All right. So this is 50 meters across, Tunguska scale. And by the way, we didn't have telescopes monitoring for killer asteroids in 1908. So this just hit the atmosphere and exploded on impact with our air, given how fast it's going.
Right.
So without these telescopes, if this hit us, it would be just another surprise air blast. All right. But we are wise astronomers today. So my question is, if it does hit Earth, is there an easy rule of thumb for how big a crater a 50-meter asteroid would make?
Yeah, it's 10 to 20 to 1. So an object that's, say, 1 kilometer across would make a crater about 10 or 20 times that size. Fortunately for 2024 YO4, it's about 50 meters across. And that's right at the size limit where the atmosphere most likely will protect us from it ever reaching the ground.
Oh.
It depends on the entry angle into the atmosphere, as to how much resistance the atmosphere puts up. And so in all likelihood, this thing will break apart in the atmosphere. The pressure wave will still hit the ground, and that's what causes the damage.
And what kind of shock wave are we looking at from, it's like you slap the atmosphere, and what would kind of be the result on, I'll say, a metropolis?
But by the way, in Tunguska, it incinerated 10,000 square kilometers of forest.
Oh my!
So that was not just the blast wave. That was the pulse of energy that showed up as photons, as light.
Nice.
Right? Am I remembering this correctly, Rick?
No, mostly it wasn't so much heat. It was mostly the pressure wave, what we call an overpressure, that would have knocked down the trees. So it was really a flattened forest for a few hundred square miles.
Why am I remembering fire?
Maybe right at the center, but that was fairly localized. Most of the damage was just trees knocked over for a few hundred square miles.
I'm going to say that's pretty impressive in terms of a disaster for a pressure wave to take out How many kilometers of trees? I mean,
Yeah, well, few hundred square miles.
that's insane because that's insane. You
But
guys
wait,
you're
Chuck,
you're both so calm about
Chuck,
this.
that's small compared with the surface area of the Earth.
Oh, yeah. It's not small compared to Northeast Philadelphia. We had one plane crash, and it took out like 3 blocks of people.
I remember that.
Yeah, that was just a little while ago. And I'm just saying, like, you're talking about miles and miles of trees being knocked. Oh, it is
Flattened.
hard.
Flattened.
It's hard to flatten a tree. That is difficult. That's no small thing.
Well, you have to remember, most of the Earth's surface is water. So this could, in all likelihood, if it came to pass, it would be over water. And they're very poor coupling between that pressure wave and the water. You wouldn't want to be in a ship underneath that, but that would be pretty easy to evacuate.
So, Chuck, I'm pretty sure,
Right.
my good fellow here,
Yes.
once the spaghetti uncertainty shrinks down to a dot, if it's going to hit Earth, we'll know exactly where on Earth it's going to hit, correct?
Recently, our capabilities have become good enough that, a small object the size of a compact car can be discovered a few days or hours before, if it's on terminal approach. And, those predictions get very well refined that they basically can tell people when to go out, hold your cell phone camera up and see a streak in the sky. And then meteorite hunters can then descend on the area to try to pick up pieces. So when we get, a precise orbit, we can be very specific about where these things are going to arrive. So
that's a scientist talking there. He says, when you know where it's going to arrive, get your cameras ready.
Right.
Rather than get your ass
Instead
out
of leave. Yeah. Get out.
No. We're going to run to, these are the sort of things we run towards. We want to get data, man. We want to pick up pieces.
Science.
This is free stuff. This is free stuff from space.
Free stuff from space. That's great.
Manna from heaven, right?
There you go.
So, Rick, where is 2024 YR4 on the Torino scale?
So 2024 YR4 ranks a 3 on the Torino scale, which means if it were to strike the Earth, it would be a localized event. And I think the important thing about a 3 on the Torino scale is that we like to emphasize that most likely when we get more data, we'll be able to reduce it to 0. And 3 is also sort of an alert to astronomers to say, let's pay attention to this object. We're not worried about it. No one is panicked about it. But let's get the data and make sure that it's going to miss.
And maybe fund a deflection program.
I was about to say, I don't want to be Makar, but what point on the scale do we have to do something? And what's the number where it's just like, hey guys, we gotta get up there and fix this?
8, 9, and 10 are the numbers you don't want on the Torino scale because those are the levels where you are certain of an impact. And YR4, if it misbehaves, it would go all the way up to 8 on the Torino scale. That would be its maximum.
Oh, because it's not massive enough to render anybody extinct. And your scale, it sounds like it's logarithmic or something, right? Or exponential. The higher the number, the much higher damage it would do, right?
That's correct.
Which is true. That's the same true with the earthquake scale. Yeah, the Richter scale.
Exactly.
Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
So if you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up. Tell us what's the latest about Apophis. Isn't OSIRIS-REx visiting Apophis?
Yes. So Apophis ties into our current asteroid story because back in 2004, it was kind of the same thing. Apophis got all the way up to 4 on the Torino scale. And in this case, we were able to find earlier images of that asteroid and refine its orbit and rather quickly have it go down to 0. So that was Apophis was the winner in terms of the highest ever recorded value on the Torino scale. But what that means, or what we found when we pinned down the orbit of Apophis, is that on April 13th of 2029, the asteroid Apophis is going to come very close to the Earth, but it's going to safely pass the Earth. And that safe passage of the Earth is at a distance closer than some of our orbiting satellites, the one out at geosynchronous distances. And so this stadium-sized asteroid Apophis is going to make a very close approach on Friday, April 13th, 2029. That Friday means nature has a sense of humor. And I've been leading a lot of efforts to try to figure out how can we scientifically study the asteroid Apophis, because the Earth's gravity and the tides that the Earth exhibits on the moon are going to tug on that asteroid too. And if we can see how the asteroid responds to the way the Earth tugs on it, we'll be able to understand how that asteroid is put together. And that's terra incognita. We've never been able to discern how the inside of an asteroid is put together.
What about a giant net? Is that
like a butterfly net?
Yeah.
You just go up there?
No. We want it to go past. So, so we'll let it go past, and we just simply want to get the most science, the most knowledge we can out of this object. Someday the knowledge of how these things are put together could be some of the most important knowledge that we've ever, extracted from a space program. And so we just want to get smart.
So as you monitor the tidal forces on it, which would serve to break it apart,
right?
If it stays together in spite of those tidal forces, that tells you one thing:
a lot more solid,
than you
right? Think.
And if it starts breaking apart,
and
it didn't have much of a matrix to hold it together.
It's a crumbly collection of cookie crumbles.
That's right. And if it doesn't care, Apophis has been around for probably thousands, if not maybe a million years, occasionally whizzing past the Earth. It's probably come closer than this in some previous millennium. And, it may say, oh, this rodeo is not really that tough of a rodeo. And it may just pass by, and Apophis itself may not care too much.
Are you guys still naming Earth-crossing asteroids that are newly discovered after gods that are in part death and destruction on the world? Because Apophis is the Egyptian god of death and darkness. I think. Right. So is that still the habit, the tradition?
There's a lot of different mythical traditions, but for Apophis, it kind of shows that astronomers have a sense of humor too.
Okay.
Yeah. Any plans to name one Trump?
Stop. Trump probably has a plan to name one
exactly.
Trump. OSIRIS-REx went on a trajectory after the sample return to intersect Apophis. Is that correct?
That's right. So NASA has approved that the next mission for this OSIRIS-REx spacecraft, which has been renamed as OSIRIS-APEX. APEX is Apophis Explorer.
Wow.
And so
Apex.
We're repurposing this spacecraft to go visit Apophis. The laws of orbital mechanics and how much propulsion we have on the spacecraft don't allow us to get to Apophis until after it's gone by the Earth. So we're going to kind of get a sort of an after shot of Apophis after the Earth does whatever it might do to the asteroid.
You're not going to touch and go on this one, right?
No, we'll leave it alone, except maybe at the very end.
Oh, you might crash into it?
Yeah, well, after we made sure where it's going to go for a long period of time, we may kind of touch down, let our thrusters blast the surface to kind of create a little crater that we can then look into. But we won't physically touch the asteroid. But I just want to say that, there's really been this fantastic cooperation with the European Space Agency, where they're working on a mission called Ramses, which would go to Apophis and get there before the asteroid reaches the Earth. And so it could be the European Space Agency giving us a before look, and then NASA's spacecraft OSIRIS-REx will give us the after look.
Because there's still a few years in there. The sample that did come back from the asteroid Bennu,
yes,
what did that reveal?
So the reason we went to Bennu is it looked like it was a very dark, low albedo, carbon-rich asteroid. And we're interested in carbon because the stuff we're made of is, carbon. We're all carbon-based units. And so this was a chance to go back and look at some of the original carbon chemistry that made the planets and ultimately made life. And we have found that very primitive carbon chemistry, even down to some basic amino acids that make up the structure of proteins and, essential for life. So we really have found sort of the holy grail ingredients of the origins of, or the chemistry that can make life.
Part of that was even expected, though, right?
Yes, I mean that's what we wanted to find. And the important thing about bringing the sample is it was collected in space. It was stored in the vacuum of the capsule, and then retrieved in pristine laboratory conditions. So we knew everything organic that we're measuring in this sample was intrinsic to the asteroid, to the space material itself, and not something introduced because the asteroid meteorite landed in a pond or in the mud, and to pick it up out of the mud and get it to a lab and things like that.
How does that compare to any other samples that we have from space?
It turns out that this kind of early carbon chemistry is extremely rare in the meteorites that we have on Earth, because most of those, it's not very strong material, and the Earth's atmosphere breaks it apart and incinerates it on the way down. And so it's very hard to collect these kind of samples in a free sample from space in a meteorite. And that's why going and getting this kind of sample was really a scientific breakthrough.
So It's implicit in what you said, but I want to make it explicit. These asteroids hearken from the beginning of the solar system, undisturbed by weather, erosion, contamination.
Right.
So
they're perfectly preserved.
Perfectly preserved. Is that a fair way to say that, Rick?
Yeah, I like to call asteroids the building blocks of the planets. They're leftover rubble, they're leftover pieces of all the material that went in to make the planets, to make the Earth.
It's like IKEA. It's like IKEA furniture. That's the stuff that's left over.
The building blocks. It's not furniture, it's the building block for furniture. No.
It's been a bit disassembled over time because it crashes into each other out there over millions and millions of years. But the fundamental pieces are still there.
So we are all of a particular handedness of these molecules for life on Earth, but some of those molecules in a mirror are perfectly legitimate molecules. We just don't use that version of them.
Right.
So, but space, if there's not something to pre-select a handedness of the molecule, you might expect it to be 50-50. I mean, and if it's not, somebody's got to answer to that. There's something doing some filtering
right, something's
there.
doing something, right.
Something's doing something. So that'd be fun to see.
That's pretty cool.
Where the future of this goes.
Yeah.
All right, so Rick, take us out with Planet 9. What the hell is Planet 9?
It's a place where I'm doing fine.
No, that's Cloud 9.
Oh, that's Cloud 9. Okay.
Pluto is the ninth planet because dwarf planets are planets too. And so
you got out of that one,
boy. Here we go.
He got out of that one.
I'm fine. I'm fine with something else being out there. But the thing that's called Planet 9 is just some indications in the data that there may be something even further out in our solar system that's been tugging on some of these other asteroids out there. There's a region out there called the Kuiper Belt. There's lots more asteroids out beyond Pluto, and some irregularities in the distribution of where all those objects are suggests there's something out there tugging on them. It's a little speculative. It could be right. It could be wrong. But, when you have an idea, you go out and search and see if you're right or wrong.
You know what would make better data than that?
What's that?
The object itself. Right? I mean, what you're saying, you're seeing all the objects that its supposed gravitational field would have influenced, and you're triangulating back on where this object must be and maybe how much mass it has. But no one has spotted the object yet, if it's real.
Right, and I think the indications are it will be something very far away, a little difficult to detect. So the jury's definitely out. But when you get these ideas, you put forward a hypothesis and you go out and test it. So that's how science works.
In the interest of getting clicks, I'm going to say it's a massive alien ship.
He's not going to agree with that.
No, I'm sure.
That's a 0, I'm afraid.
Okay.
So, Rick, I think we're done here. Gosh, it's been really
fascinating.
I'm amazed
stuff.
we haven't done this before. Our show's been on for quite some time.
Yeah.
And you demand. Oh, by the way, I don't know if anybody knows. When I get a call from CNN
Right.
about something in the solar system, I call Rick. I say, Rick, this is what I know. Is it enough? What do you know? What can I bring to this conversation?
Super cool.
So he's my go-to planet man.
I love it.
Because I was a galaxy guy.
Speed dial.
Yeah, speed dial. Because I'm a galaxy guy,
Right,
large-scale universe guy, and planets was like a whole other. That's a different species of astrophysics. You know what makes them different? They get to go there.
Nice.
Right? We don't, we're not going to a black hole or the
Right.
center of a galaxy or anything.
Right.
They get to, I wonder what that object is. Send a probe. It's like, so that's damn near experimental science.
Nice.
Yeah, and as a planetary scientist, you really put yourself on the line because you can have a hypothesis, an idea, and you send a probe there and you find out you were wrong. But that's pretty exciting when you're wrong, actually, because you have to relearn. You've gained really great insight for the things that don't prove to be what you might have expected. But I love the challenge of being able to study things that you can go there and find out if you were right or wrong.
For today's cosmic perspective, it's clear that among other interesting points of knowledge, wisdom, and insight, we've also learned that as a scientist, discovering how the universe isn't can be just as valuable to the researcher as discovering how the universe is.
It also works when you're looking for a job.
And that is a cosmic perspective. Rick, thanks for being on the show, man.
My pleasure. Great to be with you.
Love to the family. And Chuck.
Yeah.
Always good to have you, man.
Always a pleasure.
All right. This has been StarTalk, the Hazardous Asteroid Edition. Neil deGrasse Tyson, your personal astrophysicist. Keep looking up.